Hi there. All right, today we are talking about scientific notation and percent error. We're still in the section of 2.3 where we're talking about scientific measuring, okay? And so now we're just going into a couple other parts of measuring, and our objectives here today are going to be, boom, come on, rocket. Yep, all right, we're rocking it. Being able to take large and small numbers, write them in scientific notation, and to then be able to articulate the difference between accuracy and precision. Hopefully that's going to be a review for you. And then we're going to do a calculation called percentage error. And then we're going to do that in a hypothetical experiment so we can kind of see, what would our percent error be in this particular experiment. You're going to be doing something like that in one of our labs coming up. Okay, so if I were given a number in standard notation, I should be able to convert it to scientific notation and vice versa. If I'm given a set of measurements, you can tell me about which is accurate and which is precise. And if I am given an experiment and its data, you can calculate the percentage error. Okay, so scientific notation. Scientific notation is something that is going to allow you to notate or to condense, to bring in smaller, large numbers or really small numbers in terms of how much time it is to take it. Now, that's kind of notation, right? If you were taking notes, you want to write down some of what I say, not every last thing that I say. And in this case, you want to write down something that's going to make it shorter. So if I have one sodium atom and it's that many meters in diameter, what a pain it is to write all that down. Wouldn't it be much easier to write down something that was notated, something that condensed the big numbers or the long numbers anyway, and made it a lot easier to calculate? So what would that be in scientific notation? Well, it's not going to take as long to do the writing out as it is there. 3.7, and then you got to count how many zeros you go over this way, right? So you got 6, 9, 10. So 3.7 times 10 to the negative 10th meters. A little easier to write, okay? You don't lose track quite as easily. It's a good tool. Yeah, you know this tool. You've used it before. All right, so we always must express significant figures when we do scientific notation. In other words, if you write that digit down, it has been measured and or estimated, right? So it's going to be actually the known digit plus the estimated digit. In scientific notation, the digits that you show are significant, okay? Keep that in mind. And sometimes we're going to actually use scientific notation to write numbers in the correct number of sig figs, okay? Sometimes it's the only way to indicate the correct number of sig figs. You actually have to write it out in scientific notation to get it. So you really need to know how to do scientific notation. So don't just glaze over this. For instance, 50,000 kilometers, if I wanted that to be significant to the hundredths place, in other words, I've measured it all the way to the hundredths place, and I wanted to show you that, I would have to do that in significant figures. I'd have to do 5.00. Remember, trailing zeros are significant if they follow a point in the number, right? And so that would be the answer, 5.00 times 10 to the 4th kilometers. That's how you would write that number out in significant figures, correct number of significant figures. All right, so numbers that are written in scientific notation have two parts. They have the first part, which is that number between 1 and 10. That part's going to show the significant figures, and then they're going to have the exponent. That's to, something a power to the power of 10 exponent. So if I did 36,000 scientific notation, I'd do the first part, and you always want to have one number to the left of the decimal point. So it's not 36 times 10 to the 3rd, it's 3.6 times 10 to the 4th. Okay, so make sure you always do one number to the left of the decimal point, and then you're going to count over how many times you have to multiply 3.6 by 10 in order to get that answer. And I had to do that 10 times 10 times 10 times 10, 4 times, right? So that 3.6 is between 1 and 10, and it should always be that first number, whatever you come to, that should always be between 1 and 10. Just one number to the left, okay? And then, then you have that 10 to the 4th. Again, that's power of 10, 10 times 10 times 10 times 10, okay, or 10,000. All right, so let's go on. Exponent's going to tell how far and in what direction the decimal point should be moved. And I've got some cool hand motions I'm going to show you with this that'll help some of you that have always struggled with this, okay? But for the most part, it's pretty simple. If it's a positive exponent, you should be moving the decimal point to the right. So here's the decimal point, move it to the right. If it's a negative exponent, then you should be moving that decimal point to the left. So there's our decimal point, and if it's a -2, then I have to move it the other direction, right? Now I'm going to show you how to do a little hand motion to do that. So everybody take your right hand, okay? Do your right hand and you kind of make a gun out of it. Take your left hand, all right, and then you kind of do the upside down gun. I don't know if we want to call that a gangster gun or not. I'm not sure if that's appropriate. But now you make a movie box, okay? Now we're a Hollywood director and we're making a movie. Now watch what we're going to do. Our thumbs are going to indicate the direction that the exponent goes, and our fingers are going to indicate the direction that the decimal goes. So if you think about a number line, okay, let's say we have a number line that's like 10 to the third, 10 to the second, 10 to the first, 10 to the 0, 10 to the -1, 10 to the -2, 10 to the -3. Remember that your exponent, okay, is going to be going up or down, okay? Your exponent's going to be going up or down, and your decimal is going to be going left or right. So let's practice and express some of these in scientific notation, and then we'll practice with those little finger motion. The radius of the Earth, 6,378,000 meters. If I want to put that in scientific notation, now I'm going to need to take my decimal point. Where's my decimal point starting at, right? Decimal point starts right here at the end of the number. And I've got to move that decimal point in this direction because I want to have only one number to the left of my decimal point. This final thing needs to be somewhere between 1 and 10, right? And so I'm moving it this direction. Because I move my decimal point this direction, that means I've got to move my exponents up. And so how many places? 1, 2, 3, 4, 5, 6 places. And so what I'm doing is I'm going to move the decimal point 6, and I'm going to move my number up 6. Since I'm at that original place, that's 10 to the 0, I got to move it up 6 places. 1, 2, 3, 4, 5, 6. Oh my goodness, where were we? All right, 10 to the 4th, 10 to the 5th, 10 to the 6th. Oh my goodness, look at that. So when we do our answer, it's 6.378. Keep your number of sig figs the same. Times 10 to the 6. It's however many places you move that thing over, right? Isn't that cool? 1, 2, 3, 4, 5, 6. Boom. Moved it over. Decimal place moved that way, and I move my decimal or move my exponent up in that direction. All right, let's see if we can do another one. The diameter of the human hair, 0.000008 meters. Okay, so now I'm going to use my left hand. I know my decimal point has got to go in this direction because this number that I start with has to be, between 1 and 10, and it's got to have just one number to the left of the decimal point. So I'm going to move my decimal point in that direction. Left hand, right? 1, 2, 3, 4, 5, 6 places. Okay, and that means since I use my left hand, as I move it that way, my exponent has to go down. And so I'm going to have to move this over. 1, 2, 3, 4, 5, 6. We can go ahead and put 10 to the -6 down there. And I can see that I've now got a number, which is going to be 8 times 10 to the -6 meters. Okay? Isn't that cool? So you can use right hand regular gun, left hand upside down, boom, make a movie box, and you can use that. And you can use that when you're going in the other direction too. If I were going from this to this, I can do the same thing. Why and how? Well, look what I have to do. I have to take this -6 and I have to move it up to that 10 to the 0. And so how many places do I move it up? 1, 2, 3, 4, 5, 6. I move it up 6 places. That means I have to move my decimal point over 6 places using that right hand. Okay? So you can do the same thing as you're converting from one thing to the next. Pretty cool. I think it's pretty cool. I came up with it, I think. I've seen it before in other places, but I think mine is the coolest. All right. Accuracy versus precision. Okay, now you know how to do scientific notation. Accuracy is how close we are to a true value. Now, sometimes we don't know a true value, and so it's hard to say if we're accurate. But if we know a true value, if we know the actual correct value, then we can figure out if we're accurate or not. And then precision is how closely grouped things are. So are we finding answers made in the same way? And are they close or fine in a measurement? So if you remember from previous lecture how we were using, the precision of this instrument, right? Not very precise, a little more precise, a little more precise, more precise. The tiny little increments here indicate on the milliliters that you have a lot, or millimeters, you have a lot more precision than you did on that single meter stick with one line. So as you're going further and further into your measuring fineness, then you are increasing your precision. So what does that look like? Let's kind of pretend like we have a dartboard here and we're throwing darts. Which of these is accurate, which is precise, which is neither, and can we think of one that would be both or one or the other? So here is an example of one that is both accurate and precise. The darts are closely grouped together and they've hit the bullseye. In this case, we assume our true value is our bullseye. In this case, they did not hit the true value, and so they are not accurate. However, those are pretty precise. They're grouped together pretty finely, okay? This one, oh my goodness, we did not hit the target, nor did we group them together very well. So this is neither accurate nor precise. Can you think of an example that would be accurate but not precise? This one's kind of tricky. Let's think about it. Let's look at a target, and here's our bullseye. And let's say I shot a dart and I got there, I shot a dart and I got there, and then I shot a dart and I got there, and I shot a dart and I got there. Well, now it sure does not look like I did a very good job of being accurate. I definitely am not precise. But can I be accurate without being precise? In this case, I can if I think about it in terms of averages. Because look what happens. What's the average between those two dots? What's the average between those two dots? Oh my goodness, what have I hit? I hit the bullseye. And so sometimes your final answer, your average could actually be accurate even though your measuring devices were not precise. Now, maybe that's just chance, and it's not necessarily something you'd want to boast and write home about, okay? But it could happen. All right, let's talk about percentage error. It's a little hard to see this, but this says percentage error here, and it's calculated by subtracting accepted value from the experimental value and dividing the difference by the accepted value, multiplying by 100. So the formula looks like this, okay? Percentage error. Experimental minus accepted divided by accepted. Another way to talk about that, sometimes we use the term observed and theoretical. So sometimes people would be like, hey, yeah, this is observed and theoretical. Because accepted, sometimes people don't get as well, divided by theoretical. In other words, if you look in a book, okay, the accepted value is the value that you might get from a book. And you're looking in the book to see this is the value that has been found through prior research or something like that. Or maybe you did a calculation. And so in class, you did a calculation for what value you should get of this particular chemical. That's your theoretical value, or in this case, your accepted value. And then you do the actual experiment and you figure out what is it that I observed. And now you compare what you did and what you observed in your experiment with what you thought you should have gotten through the book research, okay, or through the mathematical problem, okay? So make sure you know this formula. We use this formula a lot in a lot of our labs. Of course, this year, due to our unique circumstances, we're probably not going to do very many labs, but we are going to do a lab here pretty soon called the aspirin lab, and in that lab, you're going to be using this formula. So make sure you write it down somewhere so that you have it accessible for when you come into class and we do a lab in here, okay? So what does this formula look like in action? Let's see if we can do a sample problem. Student measures the mass and volume of a substance and calculates its density as 1.40 grams per mil. Ooh, hey, key word here, calculates, okay? This is an experiment, right? He measured and he did a calculation, and it says that we actually have done some research and we have an accepted value or a theoretical value of 1.30. So now if I want to figure out the percentage error, now I have to take this calculated measured value and I've got to take that one and assume that that is my experimental, right? And so we take our observed or experimental 1.40 grams per mil, right? And then we subtract our theoretical or accepted 1.30 grams per mil, divide by 1.30 grams per mil, that's our accepted, times 100, and we get our answer, okay? So we basically have 0.1 times 100, so ooh, a bunch of stuff there, don't we have a bunch of stuff in the way? Oh my goodness, and I just lost the answer. All right, kind of hard to read there. There's an actual answer there. Divided by, so 0.1 divided by 1.30 times 100 is going to give you 7.7%. Okay, so that's the answer. Now, When we do percentages in this class, I do not need you to express percentages in correct sig figs. Maybe in your college you'll have to do that. For my class, I'm not asking you to do that. When you do percentages, just give me to the tenths or hundredths percent. Don't just leave it at 8, okay? Give me the decimal point 1 or 2 spots over. That's what I'm looking for when you do percentages. But I don't need to have sig figs when we're doing percentages. There's a way to do it, though. Just not asking you to do it. All right, our objectives. Hey, we're already done. It's a quick one today. Write large and small numbers in scientific notation. I think we can do that. It probably was a review for you, but it's never a bad idea to practice it again, right? Articulate the difference between accuracy and precision, okay? It was funny. I went to the doctor's one day, and there was a nurse, and she was measuring me. And I'm 6 foot, right, with my shoes on for sure. But she was measuring me, and she just kept being like, "You're 6'1". And I'm like, "No, I'm not." And she's like, "You're 6'1". I'm like, "No, I'm not." But every single time she was looking, and she was like this tall, and she was looking up, and she was seeing a higher measurement than I really was. So I asked her to do it a couple times, and she was very precise. She kept hitting the same number over and over again, but it was inaccurate, okay? So, this stuff actually, it becomes real, right? This is real world experience, accuracy. I was like, "Yo, nurse, you are so precise, and yet you are not very accurate." No, I didn't do that. But it would have been kind of funny if I would have. She might have been offended, though. Anyway, real world stuff, all right? Precision versus accuracy, you can express that stuff. All right, and then you need to be able to calculate your percentage error in a hypothetical experiment, and you're going to do it for real in an experiment in the lab once we all get back in this wonderful location called the science laboratory. Woo! Okay, I think that's it. Yeah, we've done our criteria. We can convert, and we can discuss accuracy, precision. We can do the calculations of percent error. We are ready to go. We're so smart, and I'm so excited to get you guys back in the classroom here one of these days soon. God bless you. Have an awesome day.